Right, so this is going to be the first part of our overview of section 1.6 on how to combine functions. And here we're going to do the algebraic pieces, adding, subtracting, multiplying, and dividing of functions. We're going to save composition of functions for the next video. All right, so the idea is that we are given two functions to start with, okay, an f and a g. Now both of these are functions of some input variable, and the functions themselves lead to outputs f and g. Now, if we're going to combine them in an algebraic way, the domain of the combined function can only exist where both functions exist. Okay? So if g has a more restrictive domain than f, the combination of them will have the domain of g, right? Where if f and g are both have restrictive domains, they're both only going to exist where both f and g exist. With the caveat that if we have this f over g, this bottom function can't be 0. The zeros don't like to be on the bottom, so we're going to have to watch for those coming up. If we are adding functions, we simply add them up. The function f plus g of x is our function f plus our function g. It's nice and straightforward like that. Subtracting, well, we know that subtracting and adding are related, so if f minus g is going to be our function f minus our function g. Multiplication, f times g is our function f times our function g. This really has interesting indications when we're talking about polynomials. And division, well, f divided by g is our function f divided by our function g. And of course we have to worry about any time our function g on the bottom is 0. Right, now let's look at a bunch of examples. So in this one we're given that our initial function f is x squared plus 1, and our g is this cubic minus x cubed minus x squared. Okay. Now when we add them up, here we're going to add these things. So when we add them up, we're going to add the values of f and the values of g together, right? So at 0, it should be 0 plus 1. At 1, it should be 0 plus 2. At negative 1, it should be 2 plus 2, so it should be up here at 4. Right? At 2, it should be 5 and whatever this thing is down here. Okay? So we'll get some nice function that it's kind of going to look something like that, maybe. Right? I'm not entirely sure what it's doing here because I don't know what my values are. Okay? But if we plug them together, okay, x squared plus 1 plus this negative x cubed plus x squared. Okay, when we add them up, remember we're adding polynomials now, so we add them piece to piece. There's an x cubed here, but there's no x cubed, so that stays where it is. There's a x squared and another x squared leading to 2x squared. There's a plus 1. Oops, I got a minus sign wrong. I always get a minus sign wrong. Why am I not surprised? Okay. All right, so this is plus 1. Okay? And we see that indeed 0 plus 1 is 1, 0 plus 2 is 2, 2 plus 2 is 4. Okay? 5 plus, it looks like negative 4. 5 plus negative 4 is about negative 1. Okay. And so this summed function has some of the properties of each. Okay. Where one of them is 0, the addition is nice and straightforward. Okay. Where they're both the same, you just get twice as much as you had going in. Okay. So that's adding of functions. All right, so in this case, we're going to take our two functions, f, which is this guy, square root of 16 minus x squared, which is a semicircle of radius 4. And our g of x is the square root of negative x. Okay. The negative x means that we take our square root of x and flip it across our y-axis. And the important thing is here is when we subtract these things, our blue, our semicircle, exists from negative 4 to 4. Our green, our square root of negative x, exists only to the left of 0. So the only things that should exist are these pieces in the middle. Okay? This is going to be our domain. All right, now, when we stick these things together by subtraction, well, since they're under square roots and addition and subtraction, they don't play nice, this is about all we can do. Okay? Now, what we see is that when this is 0, when x is 0, right, our square root of negative x doesn't contribute anything. 0 doesn't contribute anything, so we just have our square root of 16 minus x squared. Okay? Now in between, we take our semicircle that we get, and we subtract off the values that we get for our square root of negative x. Okay? Another way of looking at it is, well, it's the same thing as adding this negative square root of x. That's another way of looking at it. It's square root of 16 minus x squared plus a negative square root of minus x. Okay? Now, if we look at this as an addition like that, it gets a little easier to manage because 0 plus 4 is 4. 2 plus negative square root of 2. Okay. Negative square root of 2 is about 1.7-ish, so this should be about 1.7 lower, okay, which it is. When this is 0, the only thing we're left with is this negative of square root of negative 4, a negative of a negative 4, which is the square root of 4. Square root of 4 is 2, and we have a negative 2. Okay? So we get this thing where the domain is restricted from negative 4 to 0. All right, now let's look at multiplying things. Okay. Now here we're going to try multiplying some functions. We have this nice linear x plus 2 and this quadratic minus x squared plus x. Okay. Now one of the things that I want you to remember about multiplication is a times 0 is 0 times a is 0. So if either one of these functions, our f or our g, are 0, the multiplied thing has to be 0. So our f times g, we know that it has to be 0 at 0. It has to be 0 at 1, because those are the zeros we get from x. 0 at 0 and 1. And the zeros we get from our g happen at negative 2. 0 at negative 2. Okay? So whatever this multiplied function is, it has 3 zeros in it. 2 of them from f and 1 of them from g. Right? Now let's look at what this looks like. So f times g is going to be our f function times our g function. We can FOIL this out. Negative x squared times x is negative x cubed. Negative x squared times 2 is negative 2x squared. X times x is x squared. X times 2 is 2x. Now, we can combine our squares. Minus 2x squared plus x. Well, there was minus 2 plus 1. We're left with a minus 1. And the other pieces are just left as they are. Okay? When we multiply these together, we do see that we are 0 at negative 2, 0, and 1. So our zeros perpetuate. Okay? Now, what about being positive and negative? Now, a positive times a negative is a negative. A positive times a positive is a positive. A negative times a negative is a positive. Okay? So anytime both of them are negative, we have to be positive. Right? So below 2, our g of x is negative and our f of x is negative. Where they're both negative, the resulting thing has to be positive. Okay? In the region between -2 and 0, our green is positive, but our blue is negative. Positive times a negative is a negative. Okay? In between 0 and 1, our green is positive and our blue is positive. Positive times a positive, well, that's a positive. Okay? And above 1, our green is still positive, but our blue is negative. Positive times a negative is a negative. Okay? So if you want to keep track of positives and negatives that way, and just since it's polynomial, the only way to get from positive to negative is go through 0. You can think of it that way as well. Now let's talk about dividing functions, and let's figure out what happens when the bottom goes to 0. All right, so I've given myself 2 quadratics to work with. My blue one, x squared plus x, is going to be 0 at 0 and 1. Okay, and my green is going to be 0 at -2 and 1. X equals -2 and 1. All right. Now, when I divide, if I take this f over this g, being 0 on the top, where the bottom is some random number, some arbitrary number, has to make the thing 0, right? 0 over a number which is not 0 is 0. Okay? So at -2, right, our bottom is 0, but our top isn't. At 0, our top is 0, but our bottom isn't. So that means that we have to go through a 0 here. Okay? Now, if we're 0 over 0, a couple of things can happen. Right, 0 over 0, right? It can still blow up, depending upon how fast it goes to 0. There can be a hole, okay? But we won't know until we do these things out, okay? If it's 0 on the bottom and a non-zero number on the top, that means a blow up, right? So we're going to have a blow up here. Okay, we have to, right? Because we have a number over a 0, and the zeros are unhappy and we can't get rid of them. Here, the 0 on the bottom is unhappy, but the 0 on the top might be happy enough to get rid of it. Okay, and make it a hole and not necessarily a blow up. Now, one of the things that we can look at is the fact that our f of x, well, is there anything common in there? Right? Well, there's an x in each term. And there's always these 1's floating around. So if I pull an x out, I'm going to get a minus x plus 1. Or if I was smart, I could have pulled a minus x out, pulled minus out of both terms. Minus x times x minus 1. Okay. And our green guy can be factored as x plus 2 and x minus 1. I'm going to leave it to the interested student to do that. Okay. Now, both of these things are 0 at 1. So we knew that there had to be a multiplication that gave us those zeros. Right? That's the only way to get a 0 in a whole bunch of things that are multiplied together, is one of them must be 0. Okay? So we have an x minus 1 making g 0 at 1, and we have an x minus 1 making f 0 at 1. When we divide them, well, we're going to have the same thing on the top and the bottom, so they might actually divide out. So let's look and see what happens. Okay? So here's the resulting function. I take my f, put it on top. I take my g, and I put it on the bottom. I factor to try to make my life easier, and I see that there's an x minus 1 in each term. Okay? But I can't really get rid of it. It doesn't impact anything except at 1, because it's still constructed with something that's a 0 on the bottom there. Right? And if we're constructing with something with a hole, there has to be a hole. Now the graph isn't going to show it, but there is indeed this hole happening at -1, right? That's where we have this correspondence of our zeros of our two functions. Now, where we don't have the correspondence of the zeros, right, our green guy is 0 here. But this 0 is on the bottom, right? At -2, this thing is still an unhappy 0. And if the 0 gets unhappy enough, it's going to cause a blow up. And that's indeed what we have here. We have this vertical asymptote. Okay? Now, at x equals 0, right? At x equals 0, this is going to be minus 0 over 0 plus 2, which is minus 0 over 2, which is 0. So that's still good. The blue being 0 when the green isn't means that our function is still 0, right? We're 0 on the top, we're not 0 on the bottom. We can think of this as 0 times a half if we want. And 0 times anything is just 0. But the dividing by 0 either causes holes or blow-ups. Okay? All right. I will do an example video of composition of functions, hoping that it will be up shortly. See ya.